Okay, so thank you all for coming along. I know it's quite early, and I expect most of you got a hangover, a bit like I have. So I'm going to be sticking with English as well, so apologies for that too. But I'm here to talk about debugging and tuning multi-threaded games. I'm an application engineer with Intel, and I work primarily with games companies and middleware companies in Europe. So that's the UK as well as Europe. Okay, so the agenda for the presentation, I'll start off with an overview of why we're even talking about multi-threaded applications. We'll have a look at a case study, which is a rendered application using DirectX 9 and using a physics SDK called the Open Dynamics Engine. And then we'll go on to have a look at how this application's behavior shows up in both vTune and the thread profiler. And then we'll sort of discuss the results and open up the floor for you guys to ask questions. And if you guys have any questions as we're going through, just shout out. So before we start, actually, how many of you have written a multi-threaded application? Quite a few of you, not bad. How many of you have used vTune? One. How many of you have used Thread Profiler? None. Okay, that's what I thought. So, the overview of why we're even talking about it. Well, I guess it's fairly obvious now, but it wasn't a year or so ago, but nearly every CPU that's coming onto the market is either dual-core and now quad-core. So it's pretty obvious that there's been a big shift by the chip manufacturers to move to a multi-core architecture. And if you're in the games industry, which I know you guys aren't, then it makes sense to start thinking about multi-threading, because it's not just the PC, it's obviously the next generation consoles as well. So the Xbox 360 is a triple-core machine, and the cell processors are present in the PlayStation 3. But the other thing is that if you do move over to switching your software to trying to get some parallelism out of your software to take advantage of these CPUs, then you have to deal with some of the problems which come with that. And in the end, basically designing a multi-threaded application and having it execute so that it's completely bug-free and behaving exactly the way you want it to behave is actually not as easy as it may first look. What we tend to find is time and time again, people will tell us that their multi-threaded applications are running perfectly and that there are no problems with them. And then we have a look at them in vTune and in Thread Profiler, and they're surprised at what they see and end up potentially fixing bugs or getting extra performance. The other thing is, and I'm sure some of you are aware of this, is that there's a vast range of machines out there now. You've got single-core machines with HT, dual-core with HT, quad-core. Who knows what's coming next? And with that, you've got all these different clock frequencies, cache configurations, and, of course, laptops as well. So there's a vast array of machines to test on. So this is why it's becoming really important to make sure your threaded code is behaving the way you think it's going to behave on a range of machines, not just on the one you're programming it on, because you will get very different results dependent on whether you're running on single core, dual core, or quad core. So the case study we're going to have a look at is, as I said, it's a DirectX 9 application, and it uses the Open Dynamics Engine, and it uses the Windows thread pool to manage the threads that are being used. What it demonstrates is 3 different modes of execution: serial mode, pipelined mode, and workcrew mode. And these second two, the pipelined and workcrew, are basically techniques for threading, and we'll go over those techniques in a few slides. But what it's designed to do is to show off what the potential is of a dual-core CPU, various different threading techniques, and the Intel suite of tools. It's not supposed to be the prettiest graphics application in the world, and it's not supposed to be a demonstration of the maximum amount of physics you can do on the CPU. It's really more about the techniques involved on the threading side. So I said that there are 3 different modes of execution. Here's the typical serial mode, where you can see you've got your update world, followed by the update of the physics, followed by a render of the scene as it is at that time, and then looping round again. And this goes on infinitely. And obviously there's absolutely no speed to be gained from a dual-core CPU processing the scene like this. So the second threading methodology was the pipelined methodology. It's also known as the cascade technique. This is pretty common, actually, and a lot of applications and a lot of games use pipeline threading. And you can see that what's being done is that at the end of the update world, I kick off a thread and run the physics tick in parallel with the render of the scene. Now, obviously what that means is you have to double buffer the physics data so that the main thread can still be rendering what was there last time. But it also means your physics is one step out of sync with what you're actually sort of seeing and doing. But what we find is that that doesn't tend to be a problem for physics which is effect-based in the background. It's there to look nice, make the scene look a bit more realistic. And of course, there's a great potential for parallel speed-up by doing things that way. The thing you have to watch out for, though, is this thing called load balance. I mean, in the end, if we're threading the physics against the render of the scene, depending on which one takes longest, this will determine the critical path of the frame. So if you only have 5% of your time spent doing physics, you're not getting much parallel speed up for a start, and secondly, you're totally bottlenecked by the render. And we'll see how this shows up inside a VTune and thread profiler. So the other technique I mentioned before was the work crew technique. And basically what this means is rather than having a fixed synchronization point where we take the update of the physics tick, we just simply take the result when it's ready. Now, this is a little bit harder to implement because you have to figure out, when you're going to try and pick up the result of the physics, what you're going to do if you haven't got one there. And so that could lead to issues surrounding interpolation. In this application, I haven't bothered to interpolate the results, so I just take it at the beginning of a frame if it's ready, and if it's not, then I just carry on with the previous data. And of course, this does mean that in the end you could render the same frame twice with the physics, but because we've allowed the render thread to just run off as fast as it can, it's taking physics results very quickly, and it's pretty hard to tell that that's actually happening sometimes. But gives you a great opportunity for parallel speed up because you don't spend time with one thread blocking the other. And as I said, we'll see how those two different techniques show up in VTune. I also mentioned that the application uses a thread pool, and basically a thread pool just allows you to queue off a load of tasks for functional parallelism, and as threads become free inside the thread pool, they'll take up that function pointer you've passed in and execute those threaded functions. And there's a very simple way of accessing this. It's just queue user work item and pass in your function pointer. It's a very quick way to get up and running with threading without really having to get your hands dirty. So it's a very quick way to get going. Okay, so I'll show you the demo running at this point. Okay, so as I said, we've got a DX9 application. So that's it running single-threaded. And that was it running multi-threaded. I'll just reset the graph. So I also have a graph up here. Oops. So what the graph's actually showing, so the vertical axis is the time in milliseconds. The red line basically was the multi-threaded pipelined version, and you can see it's taking significantly less milliseconds each frame to complete. And I think for every one of those frames it was always faster than the single-threaded version. But also what I wanted to show you was that, so that was, the red line was effectively the pipelined technique. So if we switch off the pipelining and rerun it, so the blue line is the work crew technique. And you can see that most of the time, apart from that spike, which was probably something kicking off in Windows in the background, it's actually right at the baseline there. And that line, if you think about it, represents the time it took for the render of the scene, because The render loop never waits for the physics result. It only takes it when it's ready. So the physics result can never impact on the frame rate. And so you can see the blue line basically is what the cost of the render was. And the interesting thing to note then is that the red line, after a very short amount of time, actually meets the blue line and stays there, which means to start off with, the physics workload was higher than the render workload, but after a while it was actually less than the render workload. And we'll see how that shows up in VTune. Does anyone have any questions at this point? Don't be timid. Okay, so we'll have a brief introduction on the VTune Performance Analyzer. So basically, VTune has three main modes for you to use as a profiler. The first one, and most commonly used, is the sampling load. And this allows you to have a look at, to basically perform a system-wide analysis very quickly with low overhead. So it doesn't really change the performance of your application. It gives you the chance to have a look at the hotspots, both per module, per thread, per process, and right down to function and source code level. And there's also a new feature in VTune called the sampling over time feature. And this gives you a little, effectively a graph showing you how, over time, how expensive your function was, or rather your program was. And we'll see that in action in this particular program. So also there's something called call graph as well, which is particularly useful if you don't know the design of an application, because you can run call graph over it and have a look at a flow diagram of how the program was executing. This is particularly useful because if you haven't written an application and you do a sampling session and you have a look and 80% of the time is going in one function, you don't really know whether that function was called once or a million times. And call graph will give you that information. So you can then look up that function in call graph and see algorithmically how it's situated in the program. So it's very useful for that kind of thing. There's also a counter monitor for detecting things such as context switches, but many other things too. So I want to go over some of the basic steps on how to set up VTune, actually, because I find that time and time again when I'm visiting developers, even if they've had VTune for a number of years, they still don't set it up the way that we generally set it up. So I just want to go over this stuff. It's fairly obvious, really, though, but for a graphics application, you probably want to try and remove fill rate from the equation. That's the first thing to do. So down-resing what you're profiling so that you're not being bottlenecked by the GPU, which, to be honest with you, it's very possible to happen if you're running at 1900 by 1200 with full scene anti-aliasing switched on. You probably are fill rate limited, so it's worth just knocking it down. The other thing which can make things easier for you is running in windowed mode. The reason I say that is because in a game or a real-time 3D application, usually the bit you want to profile is not the loading of the assets or something like that, or the front end. It's some bit of action inside the actual game, and you just want to take a snapshot of that. So running in windowed mode will help, and we'll see why in a little bit. The other point is obviously to make a release build of the application and create a program database. So we advise against doing that and prefer you doing that. Okay, so the first thing which a lot of people forget to do is this one here, no application to launch. A lot of people don't tick that box and they point VTune at their program. And so when you click on Start in VTune, it starts your program up, profiles all the loading, everything else, all the information you're probably not that interested in. So all you have to do is click on No Application to Launch, and then modify the default configuration. And configure it, and set this little delay of, say, something like 5 seconds. This is so that when you start the sampling session in VTune, you can switch back to your application and give Windows a chance to actually perform the context switch and be sampling your application as if it was running as the main process. And of course, you can click on the Events tab and sample for lots of other things other than just clock ticks. And then so what I recommend is setting it up like this so that you've got VTune probably at the bottom of the screen here with the output window visible. The reason that's useful is you can see that the delay has kicked in and when it's resumed sampling. Okay. So you just click on the sampling wizard. I'm going to choose a slightly smaller delay because I know I can be quick with this. And since that simulation doesn't take 20 seconds, it only takes about 10 to complete, we'll drop that down as well. Okay. So basically what I'm going to do is I'm going to sample the application running multi-threaded with the pipelining switched on and with the pipelining switched off so that we can have a look at the difference in results in VTune. So let's switch the threading on. Okay. So when the delay stops, we sample. So you can see how fine-grained we got there with that sampling. We really did only sample the bit we were really interested in. And before we look at the results, we'll kick off another session. And as soon as that delay is stopped, okay. So the first one is the pipelined one. And you can see this is the sort of classic layout you might expect with a 3D application. You've got a fair bit of time spent in the main application, 33% there, but there's quite a lot of time in the ATI driver. That's the system idle process, D3D. But what I'm interested in showing you guys, so if we click on the process tab and then make sure your process is highlighted, and then this is the sampling over time view I told you about. And basically this legend down the bottom gives you an indication for scale, but obviously white and light green mean very few clock ticks, and red means a lot of clock ticks. And up at the top on the right-hand side, you can see the application starts off with not so many clock ticks, and then as that physics simulation kicks in, we get a lot of CPU work going on. Now the interesting thing is we can click on threads there. So we've now got the two threads that were running. So thread 2 will have been the main thread because it was busy from the word go. And you can see that it actually turns a paler shade of green as the physics starts. So if you look at where the mouse is, this region here, you can see that it really goes very quite light green as the physics kicks in. And that's some of the impact that the physics thread is having on the main thread. And it's very visible in this kind of graph. This feature is fairly new in VTune, but I think it gives you a very quick and rough way of looking at how your threads are interacting. And if you didn't expect that to happen, then it tells you that you could probably follow up with something like the thread profiler and try and find out why that thread's being impacted. So in contrast, if we have a look at the work crew technique, similar sort of layout at the module level. So we'll click on the process, and then so that looks the same, doesn't it? At the process level, everything looks the same. But at the thread level, it doesn't look the same, because you'll see that once again, thread 2 is the main thread. You can see that basically it never turns a lighter shade of green. And even when the physics kicks in, it doesn't really change at all. So you can really see the difference showing up in VTune there of how those threads were working. I just thought I wanted to show you that new feature because I think it's something which it's really very, very useful. I mean, if we click on the module view, you can see it over time with the modules as well. So really can, in a way which isn't so easy to see just from looking at the normal bar charts you get in VTune. This is a little bit more visual. And if you're looking for something over time, then this is the way to do it. You can actually also tie a thread profile run to a VTune run as well. And it's not covered in this session, but you can really try and map the results backwards and forwards. Okay. Does anyone have any questions? Okay, so I'll introduce you guys now to the thread profiler. So basically, the thread profiler tracks thread performance in applications, and it's compatible with Microsoft Win32 API, OpenMP, and POSIX threads. It gives you several things. It's basically a plug-in to VTune. I'll show you how to set it all up in a little while. But it gives you a breakdown of the critical path. So obviously, changing the length of your critical path will absolutely guarantee you gain some performance. So being able to see how the critical path is formed in your application is quite useful. It also has various other views as well. It will give you a view of the concurrency level you're achieving, so that's how many threads are active at the same time. It'll give you information about impact from synchronization objects and actually show you which synchronization objects were causing the impact. The most useful view, I think, is the timeline view, because this actually shows you your thread creation and destruction and how threads are causing impact to other threads, and will actually show you which thread is impacting another thread. And from that view, you can actually right-click on impact and drill down into the source code and see which synchronization object or which event it was which caused the impact. So it's an extremely useful tool, and it doesn't affect the application performance that much either, unlike CallGraph. So how you set it up, basically, as I said, it's a plug-in to VTune, and you just need to click on that category drop-down list and select threading wizards, and then the thread profiler. You do need to launch your application. It's basically, we need to track the thread creation, so we need to have it launching your application. But in the end, you can ignore the serial time you'll see at the start, which is your application loading and all the rest of it. Okay, so let's see it running. So we just select threading wizards, thread profiler. So we're going to launch an application. Okay. And so this will actually start the thread profiler off. It's doing a binary instrumentation. So I just switched on the threading and kicked the simulation off. Okay, now before we look at the results, I'm going to start another one off. And this time switch the pipelining off. Okay. So we've got two sets of results. The first one is the pipelined one. Now what I want to explain to you is, if you look at where my mouse is, the top view here is basically a statistical representation of what you see in the lower view, the timeline view. And you can see that we have a load of serial time at the start of the application there. That was before we actually started the, that was basically the loading of the assets, the application startup time. And you can see where we start to get some real thread activity is where the physics really kicked in. So what we can do in this view is we can decide to drag. And so you can see that the graph at the top changes. It's the bar chart at the top, sorry, changes. It's statistically linked to this. And what you can see is that was where the threads were first created, and that's a good view of what's actually happening in the application. So you can see at the top here, it says that 64% of the time is spent in parallel, fully utilized mode, so that's at concurrency level 2, but we've still got 35% of the time spent in serial. And remember, I have dragged it to a section where we really were doing the physics as well. We're not including the startup time here. And you can see it on this graph below. This darker green bar is proper active work. And you can see we've got proper active work here, but it's lasting much longer than the render. And that's where you're getting your impact. And you can even see there, it tells you that there's a manual reset event that's causing that. And oops, excuse me. So we can right click and drill down, even down to source code with that. So it's now shown you how the impacts occurred with the two different threads. So the top one is the set event, and that is inside the physics thread proc. So that's basically the event which was causing the impact, and you can see on the other thread that's where we were waiting for the event. So it very clearly shows it up in Thread Profiler, which is really handy because if you see some weird activity between threads and you weren't expecting it, you can just drill straight down to the source code and see where it came from. And some other programmers put a strange weight in there that you weren't expecting. Okay. So the other thing I wanted to show you was you've got various different things here in Thread Profiler. We can switch on behavior, which behavior will tell you a little bit more about the critical path. And you can see that the red here is impact on the critical path. So all of the time spent at concurrency level 1 was slowing down the application. And if we have a look at the behavior on this, yeah, again you can see here it is. Here's the impact that we're talking about, because the main thread is waiting for the physics. So that's how it looks with the pipelined mode. If we switch to the work crew mode, let's once again drag in so that we're looking at some real work and not the load up time. So here you can see things have changed, haven't they? We've got 81% of the time spent at concurrency level 2 now, and only 20-odd% spent at concurrency level 1, so we're getting much better CPU utilization. We can definitely tell that for sure. And if we switch on the behavior, look, there's absolutely no red there at all. There's no impact to the critical path. That's because the main thread's never waiting anymore. And if we look at this graph down here, you can see that we're getting much more overlap of parallel work. That orange section is considerably smaller than it was before. And if we look at the behavior, there's absolutely no red on the graph there. The main thread is absolutely the critical path now because it's never waiting for the physics. So you can see how both VTune and Thread Profiler are sending out the same messages. They're both agreeing with each other, and from what we understand of how the application is working, this stuff is all tallying up. Okay, so basically what VTune showed us, which is why we switched to Thread Profiler, was that there was impact being caused to the main thread. And you could see that with the work crew technique that had pretty much disappeared. Yeah, once again you can see the concurrency and behavior. So I took this with the serial mode as well, and you can see that as you would expect with serial mode, everything's at concurrency level 1. That was the pipelined mode, where we're definitely getting some fully utilized behavior, but we've still got a lot of serial time as well, and it does definitely impact the performance of the application. And you could see that, you could see that in the timelines as well. But with the work crew technique, yeah, you get much better utilization and no impact to the critical path. And the timeline views showed that off as well. So basically, yeah, to wrap up with that then, basically if you want to get the best out of a dual-core or a quad-core CPU, you need to do some threading work. It's not a free lunch anymore, you have to actually do some work. And really, in order to keep this stuff so that it's bug-free and running as well as you can, then we really do think you need to use tools for the jobs, because it's very hard to actually see how your threads are really interacting without some kind of graph showing you how they're interacting. I know I work for Intel, and I'm not trying to sell the tools too much, but there aren't many profilers out there which deal with threading as well as vTune, and I don't know of anything like Thread Profiler on the market. So these are really very, very handy tools. There's also another tool which I haven't mentioned here called the Thread Checker, and this basically allows you to track things like race conditions and deadlock, which can be a real nightmare to find in threaded applications. But it's probably a whole talk on its own, the Thread Checker, which is why I left it from this presentation. You can get trial versions from this website if you fancy testing out the tools. I encourage you to have a go with Thread Profiler. It really is very useful. And if any of you guys have got applications where you're trying to push a dual-core or quad-core CPU quite hard, we're always interested to hear what you're doing. So basically come and talk to us if you've got questions about things like that. Okay, so does anyone have any questions? Yes?
Hi. Do you have function level profiling where you can see which functions are taking the most time and how they influence each other? Because multi-threading might mean that they slow down each other accessing some resource.
Sure, yeah. vTune has... so the question was, do we have functional level hotspot analysis? Is that the question? Yeah, vTune provides support for this. It has done actually for many years. Basically, you can see your hotspots by function. And what we recommend you do is do a sampling run, have a look at your hotspots by function, and then have a look at the call graph and see whether that function sits inside the call graph to see whether it's an algorithmic issue or whether it's really the function itself.
Just a clarification, can you see how they influence each other as well? Because the hotspot function might be a hotspot because another function is running at the same time.
I see what you mean, but that won't be... the sampler won't pick that up as time spent in that function, because the sampler will basically have a look at what code is running. That's how the sampling works. So you won't get the issue that you're talking about, where I think what you're suggesting is if another thread kicks off and basically takes the focus away from the main thread, for example, the sampler won't pick up that time is being spent in that thread. It's going to pick up the time spent in the other thread that's running. So your hotspots are still going to look right. If you do you follow me?
Okay, I think we can have a big conversation about that, so we will have later. Thank you.
Thanks. Yeah.
What about third-party libraries? I may not have the source for them, and maybe they use some sort of allocation or locks or whatnot. Does it show up in vTune? What can I see?
So the simple answer to that is for a lot of libraries or people providing third-party software, if you speak with them nicely, they'll give you the symbols. Microsoft certainly provide them for the OS and for things like D3D. So a lot of the major big libraries you can get the symbols for and have a look at how that shows up in vTune. It is particularly useful because if you find your application's got a lot of time spent in the kernel, you might want to have some time, some explanation as to what's actually going on there and what in your application is triggering it. So you can get hold of symbols for some things. For the other things, well, it's kind of difficult to work out what's going on. Anyone else? Okay, thanks for listening, guys, because I know it's early.